In this lecture, I'll discuss about rank of a matrix, row reduced forms, and solving a system of linear equations. First, let me define rank of a matrix. So here is the definition. A matrix is said to be of rank R when, number one, it has at least one non-zero minor of order R, and number two, every minor of order higher than R vanishes. So just by finding the minors of the given matrix, we can find its rank. I'll take up an example and I'll show you how we can define the rank of a matrix by finding the minors. So to find the rank R, so we have to verify these two conditions. So it has at least one non-zero minor of order R, and every minor of order higher than R vanishes. So we know how to obtain the minors. Minors will be obtained by deleting R columns and R rows and R columns. So here P is a matrix of order 3 cross 4. Okay, here for this matrix we obtain the minors of order less than or equal to 3. Less than or equal to 3 means we will obtain the minors of order 2 as well as 3. So 3 is greater than 2. So according to the definition of rank, the minors of order 3 are zeros. So how many minors of order 3 we have? 4 minors, right? So we'll obtain the 4 minors by relating the R rows and R columns. So the minors of order 3 are zeros. So if we expand this determinant, we will obtain zeros. So there is a minor of order 2 in this matrix whose determinant is not 0. And that minor is 1, 2, 2, 3. So if we expand this determinant, the value is not 0. Hence we can say the rank of the matrix P is 2. This is how we can find the rank using the definition. So what we have to do is we have to consider the minors of order less than or equal to the given order, and we can obtain its rank. So I'll take few more examples to obtain the rank. So sometimes we can reduce the matrix and then we can find the minors and we can define the rank also. I'll take up such examples. In the first problem, 1, 2, 2, 1, 2, 3, 1, 4, 2, 2, 6, 5 is the given matrix. Let us denote this matrix by A. Before finding the minors, I'll just reduce this matrix by using elementary row transformations. So the suitable transformations here I can use is R2 dash is equal to R2 minus R1, R3 dash is equal to R3 minus 2 times of R1. Okay, so then A is equivalent to the matrix, keep the first row as it is. Now we'll obtain the second and third row as new rows. So the difference is 1 minus 1 0, 4 minus 2 is 2, 2 minus 3 is minus 1. Then applying the second row transformation, we get 2 minus 2 0, 6 minus 4 2, 5 minus 6 is minus 1. So here we can see the two rows are equal. They are identical. Hence the value of this determinant is 0. So we can say the minor of order 3 is 0. The determinant of the minor of order 3 is 0. So, and we can obtain the minors of, because the matrix is of order 3 cross 3. So we have a minor of order 3 and a minor of order 2. So after reduction we obtain the matrix wherein the two rows are identical. So according to the property of determinants, its value is 0. So there is a minor of order 2 whose determinant is not 0. So we have to obtain that determinant. We have to obtain that minor. Here that minor is, we can see we have so many minors, that is 1 2 0 2 2 3 2 minus 1 0 2 0 2 2 minus 1 2 minus 1, then 1 3 0 minus 1. So like this we can have the minors of order 2. So all the possible minors we can obtain. So of these minors, there is a minor of order 2 whose determinant is not 0, and that minor is 1 3 0 minus 1. So you can write all the possible minors and you can find their determinants. If any of the minor of order 2 is not 0, then we can say the rank of the given matrix is of order 2. Here I have not written all the minors. Here I have written the minor whose determinant is not 0, that is 1 3 0 minus 1. If we expand this determinant, we obtain its value as minus 1, which is not equal to 0. So therefore, according to the definition of the rank of the matrix is the order of the minor. So the order of the matrix, that is 2 cross 2 minor matrix. So it is 2. This is how we can obtain using the definition, and one such method we will discuss, that is by reducing the matrix into the echelon form, wherein just we have to count the number of non-zero rows. So you can go with the definitions or you can find the rank by reducing the matrix into echelon form. So I will take you to that part. So finding the rank by reducing the matrix to echelon form. So as all we know what do we mean by echelon form. So let us define the echelon form. A non-zero matrix E is said to be in the echelon form if the following conditions holds. Number 1, the first few rows are all rows of E or non-zero rows, and the remaining rows, if any, are zero rows. The second condition, the first non-zero element in each non-zero row after the first row appears in a column that lies to right of the first non-zero element in any preceding row. That is, this is how an echelon matrix will look like. There may be a first few non-zero rows and other rows may be zero rows. That means echelon form is nothing but the matrix will be reduced to upper triangular form, wherein always the leading entry should be 1. After reducing the matrix to echelon form, we can compute its rank. That is, the rank of the given matrix is equal to rank of the echelon form, which is equal to number of non-zero rows in E. Just we have to count the number of non-zero rows in E, which gives the rank of the given matrix. Let us find the ranks by considering the following examples. Number 1, A is a matrix of order 4 cross 4. It is 2, 1, 3, 5, 4, 2, 1, 3, 8, 4, 7, 13, 8, 4, minus 1, minus 1. Here, let us reduce the matrix A to echelon form. We mean there may be number of non-zero, first few non-zero rows and other rows may be zeros. So in turn, reducing to echelon form is nothing but reducing the matrix to upper triangular form. So we have to make all the elements below the diagonal to zeros. So let me have the row transformations here. So by identifying the elements below the leading entry, we can have the transformations, row transformations, right? See, the element of the first row is 2, where the elements below this leading entry are the multiples of 2. So here we can consider the row transformations in the form R2 is equal to R2 minus 2 R1, R3 is equal to R3 minus 4 times of R1, and R4 is equal to R4 minus 4 times of R1. By identifying the elements which we have to make it to zeros, we have to consider the row transformation. Please remember this. Now applying these row transformations, okay, to second, third and fourth row, and we get the new rows as the first row we have to keep as it is. The other rows will changes to 0, 0, minus 5, minus 7, 0 0 minus 5 minus 7, 0 0 minus 15 minus 20. Now you just observe the new rows which we have obtained by row transformations. The second and the third rows are identical, and the fourth row is a multiple of 3, 3 times the second or the third. So that means we can easily make the third and the fourth row as completely zeros, right? With the help of row transformation, R3 is equal to R3 minus R2. Just we have to make the difference. Then R4 is equal to R4 minus 3 times of R2. So that we obtain the equivalent matrix as 2 1 3 5 0 0 minus 5 minus 7. The last two rows are zeros. So according to the definition, we can say this is in echelon form. This is an echelon form wherein first few rows are non-zeros and where the elements below the leading entries are zeros and the other two rows are zeros. So therefore, rank of the given matrix is equal to rank of the echelon matrix, which is equal to number of non-zero rows, that is 1 and 2, hence the rank is 2. This is how we can obtain the rank by reducing to echelon form by using a set of row transformations. Next, I'll discuss about the system of linear equations. So how to find the solutions of homogeneous or non-homogeneous system of equations by transforming into the matrix equation and by applying a set of elementary row transformations. So first let me define what we mean by a system of linear equations. So let us consider a system of m simultaneous linear algebraic equations in n unknowns of the following form. So that is this. Number one is called a system of linear m equations in n unknowns. We don't know whether one is homogeneous or non-homogeneous. So the system is always in the form a11x1 plus a12x2 plus and so on plus a1nxn is equal to b1, a21x1 plus a22x2 plus and so on plus a2nxn is equal to b2, and so on. am1x1 plus am2x2 plus and so on plus amnxn is equal to bn. So in the system 1, x1, x2 and so on xn are unknowns and a's and b's are real known constants. So we have to obtain the unknowns x1, x2 and so on xn. So the system 1 is said to be homogeneous if all the bi's are zeros. Otherwise it is a non-homogeneous system. So the solution, the set of values of x1 to xn that satisfies all the equations 1 is called the solution of the system 1. So we will have that solution by forming the system of equations 1 into the matrix representation or the matrix equation. So let me have a matrix representation of the system 1. So let A denote the matrix formed by coefficients A's present in the system 1. Let X denote the column matrix formed by the unknowns, and let B denote the column matrix formed by B's. That is, A is equal to all the coefficients of the system 1, all the coefficients of X, that is A11, A12 and so on, A1n, A21, A22 and so on, A2n and so on, AMN, AM2 and so on, AMN. X is a column matrix consisting of all the unknowns x1 to xn, and B is the column matrix which will have all the elements of the RHS of the system 1. So X and B we say the column vectors. So with Ax and B defined as above, the system 1 can be expressed in the following matrix form. That is, always we write the system 1 in the form Ax is equal to B, Ax is equal to B, and this is called the matrix representation or the matrix equation of the system 1. And also we can have the augmented matrix of the system 1, which is denoted by in the square bracket A hyphen B. So it is the matrix formed by appending A to an extra column consisting of the elements of B, is called the augmented matrix. To solve this system, I'll discuss one such simplest method called Gauss elimination method, wherein we have to start with an augmented matrix and we have to reduce the matrix A to lower triangular matrix from which we obtain the solution. Here I'll explain you the Gauss elimination method by considering a system of three independent equations with three unknowns. That is, a11x1 plus a12x2 plus a13x3 is equal to b1, a21x1 plus a22x2 plus a23x3 is equal to b2, a31x1 plus a32x2 plus a33x3 is equal to b3. For this system, I will write the matrix equation or the matrix representation as Ax is equal to B, where A is the coefficient matrix and X and B are the column vectors. So in the augmented matrix, what we have to do is we have to reduce the matrix A to an upper triangular matrix. That is, we have to make the elements A21, A31 and A32 0 by row transformation. What are the operation we'll use to reduce the matrix A? The same operation we have to use for an augmented matrix also. Then we obtain the equivalent matrix like this. I have shown all the equivalent matrix by writing the elements with dashes. Easily you can see. See, finally, after a row transformations, the matrix A. See, this is the coefficient matrix, right? This is the coefficient matrix, and this complete matrix is called as the augmented. But we have to observe for the coefficient matrix, where all the elements below the principal diagonals are zeros. Hence, we can stop at this stage and we have to write the solution now. So after reducing the matrix A to an upper triangular form in an augmented matrix, we have to write down all the linear associated equations with the reduced form obtained in step 1. And we obtain the solution by back substitution. Okay, the last row gives the value of one last unknown, that is say z, and the second row gives the second equation gives the solution of the second unknown y by substituting the value of z, and the first equation gives the value of x, first unknown, by substituting the value of y and z. So this is called the back substitution. See, here I have explained. Let the number of equations in the reduced system be equal to r. Okay. So if r is equal to n we mean the number of unknowns, then the system yields a unique solution or a unique solution. we call that solution as unique solution. If number of equations, system of equation is equal to number of unknowns, then the system will have a unique solution, and we obtain that unique solution by back substitution. If suppose r is less than n, the number of equation is less than number of unknowns, then we can choose n minus r unknowns in the reduced system. I'll take one such example. Solve the following system by Gauss elimination method. Here I have set of three linear equations with three unknowns. Let me consider first the matrix representation. X is equal to B and an augmented matrix AB, and I'll reduce this matrix to an upper triangular form by using a set of row transformations. The operations we have to apply to an augmented matrix, but the elements of the coefficient matrix A below the diagonal entries are zeros. That means we have to reduce the coefficient matrix A to upper triangular form. See, after a set of row transformation, here the equivalent matrix is 1 2 3 1 0 minus 1 2 0 0 0 minus 4 2. Here we can say the coefficient matrix, say after the elementary transformations, the coefficient matrix is an upper triangular form. So therefore, in this case, the number of non-zero rows are 3, and also we have the number of unknowns 3. Hence this system possesses a trivial solution, and we obtain the solution by writing the equivalent system of equations of this reduced matrix, that is x plus 2y plus 3z is equal to 1 minus y plus 2z is equal to 0 minus 4z is equal to 2. See, just by back substitution we get the solution. From the last row we have the value of z. From the second equation we obtain the value of y, and in the first equation we can have the value of x. So therefore this system possesses a trivial solution because number of non-zero rows is equal to number of unknowns. I'll take up an example wherein number of non-zero rows is not equal to the number of unknowns. Yes. So in this system of equations, x minus y plus z is equal to 2, 3x minus y plus 2z is equal to minus 6, 3x plus y plus z is equal to minus 18. Let us obtain the matrix equation x is equal to b and an augmented matrix AB is equal to 1 minus 1 1 2, 3 minus 1 2 minus 6, 3 1 1 minus 18. So let us reduce the coefficient matrix to an upper triangular form by using a set of row transformations. So usually you can have the row transformations with the help of the elements which will have to make to zeros, right? So here these three entries we have to make it to zeros, the leading entry and this entry. So after a set of row transformation, we obtain the equivalent matrix as 1 minus 1 1 2 0 2 minus 1 minus 12 0 0 0 0. See, here the number of non-zero rows of A are 2, and also the number of non-zero rows of an augmented matrix is also 2. So we can say the non-zero rows is less than number of unknowns. We have 3 unknowns, but we have only 2 equations. So therefore here we can choose n minus r unknowns arbitrary. That is, one unknown we can have arbitrarily. So I will choose z is equal to some k, or we can take z is equal to, because the system possesses infinitely many solutions. So in general we can take k is equal to that is one unknown is equal to k, or 1, 2, anything we can choose. I'll take z is equal to k so that I'll obtain the other unknowns y and x in terms of k by back substitution. This is how we can have the solution by Gauss elimination method when the system not possess a trivial solution. And also we can say the rank, right? R has rank. If rank of the matrix A is equal to rank of the augmented matrix, and if it which is less than the number of unknowns, R represents the rank, isn't it? So n minus R unknowns we can choose arbitrarily.